All right, so welcome again. Like I said, my name is Scott Enigson. I'm a solutions consultant here with Alteryx. And today, much like last week, we're going to be talking about predictive analytics within Alteryx, specifically regression modeling. Like last week, this session is meant to kind of be at a demonstration pace, so you're more than welcome to follow along. But I'm not going to stop necessarily for questions along the way. So if you miss something, there's a recording that will be available at the end of the session. If you do have a question or need to communicate with me during the session, you can use the QA panel or the chat window within your WebEx. I have my colleague Joe Miller here monitoring that, so hopefully he can get any issues that you have straightened out. All right, so moving along here, this is part of a training session that runs every Tuesday at 10 a.m. Pacific. We have some upcoming sessions. Next week is a tips and tricks session, which I would personally recommend. You can always lots of useful information to pick up in those classes. And then we're going to be starting a new intro series. So there's a good 6 classes here, and every week on Tuesday, followed by a few additional ones where we are really going to be starting from scratch. It's a really good course. If you know anyone who's brand new to Alteryx, I highly recommend having them partake in those classes. We're also going to be adding some Thursday classes into the mix. So to complement those introductory classes, we'll have a number of additional training sessions on Thursdays that are a little bit more advanced, some really advanced, so that those who aren't beginners still have options for training classes. Okay, so today we are going to walk through a model build and assessment. We're going to use the data that we created last week, and we're going to build a couple of models for that data. All right, the business case, if you remember from last week, we created those 2 data sets. The focus primarily was on the data investigation tools, prepping the data, getting it ready. The goal or purpose there was to identify which variables would be most important in a model building phase, and that's what we're going to do today is actually use that data to build these models. The first model is going to predict the average consumer expenditure each household will spend on food away from home. If you remember, that was one of the variables in that data set. And the second one is more of a target marketing example where we will predict whether or not a household is likely or not likely to be a customer of ours. So that's the business case going forward. Again, if you missed last week's class, it is available for recording out on alteryx.com/training. All right, a couple of modeling techniques that we're going to focus on today. Linear regression, logistic regression, and decision trees. The 2 regression models are quite similar. The linear regression model is going to take create a predictive value for your target variable. And then it uses the weighted sum of all of the predictive variables that you throw into it in order to, and they will add up to the sum of those will add up to that predicted value for your target. The logistic regression is a similar idea, except that it's going to create the probability because it's not necessarily a numeric value. You're saying yes or no, will this person be a customer? So it's the probability of them A being a customer or B not being a customer. The decision tree is pretty flexible. It's basically, it buckets your data and determines which characteristics of those buckets make the most sense in your model. It's going to create a series of kind of if-then rules that end up telling us something about people with the certain characteristics. And these will make a lot more sense once we really get into the guts of things. And lastly, what we'll do at the end of each one of these is we'll score the best model in each scenario and see what our results look like. So with that, we will jump into Alteryx and start building our first model. Okay, so the first model that we're going to do is a linear regression model, and we're going to work with the restaurant expenditure data that we prepared last week. So the first thing I need is an input tool, and I need to go out and open up that data set from last week. If you remember, it was the RE_model input file was the data we brought in. So if I connect out to that, now, remember, normally you're going to spend a lot of time doing your data prep, up to as much as 80% of your time. We already did a bunch of that last week in our session, plus there was some that was done beforehand. We did things like, with our educational attainment, we recoded them so that when they appear on a chart, they would be in order. So we added the number kind of in a sequential order of progression as you get more and more education. We created a couple of new variables here at the end. We created a college degree variable, just a simple 1 or 0 for yes or no, you have a college degree. And we did the same thing with married couples with children. So we kind of combined the family structure with the children variable to create a yes or no for do you have a married couple with children. So that's a lot of the data investigation. Today we're going to focus on building the models using that data. There's going to be a lot of methodology as part of today. There's a lot of resources out there for you to get additional help on that methodology. In this session, we don't have time to get really into the weeds of statistics. This isn't meant to be a statistics class, so please bear with me if you don't completely understand the methodology. There's plenty of resources. Just going into the Alteryx help will get you just about as far as you need to be. Okay, so with that said, we will go into our predictive tool set here up at the top, and we're going to pull out our first tool, which is the linear regression. We'll connect that up to our data set. Okay, so typically as a best practice, you would want to, in modeling, you would want to sample out your data. But in this case, we're not going to do that here, but we will do that in the next example. So inside the linear regression tool, these are all the modeling techniques that are available. They're all built out very similarly. You're going to start off by giving your model a name. In this case, we're going to call it our lin mod. Okay. Then what we need to do is we need to select the variable that we want to predict, which is our target variable. Okay, so you see here, I only have 4 choices, and that's because linear regression can only be used to target a numeric variable. Okay, so you see our food away from home, which is what we want, is here, but things like educational attainment, family size, those string variables aren't there to be chosen as options. So you don't necessarily need to know that linear needs to be numeric. It helps, but it certainly won't let you plug the wrong variable type into this model. If you know that you're predicting food away and you don't see it on this list, chances are good that maybe it has the wrong type stored in the database. So maybe go back a step and check to see that that is in fact a numeric field coming through. Next, we want to select our predictive variables. All right, so we have all of our predictive variables available. In the linear regression model, you have complete control over what goes into the model. It's not automated in any way. It's completely up to you to decide which variables you want to use. Now, this can be a pro and a con, and as you'll see with all the modeling techniques, they all have pros and cons. A pro here is that it's completely up to you. You have complete control over which variables you want to be part of predicting. The con can be the same thing. You have complete control, so you have to decide which variables you want to use versus which ones that you don't. So the first time through here, we're just going to pick all of our original variables. So I'm going to grab income, age, education, family size, family structure, children, and urban. Because these two new variables are linear combination of some of these other variables I already have, we're not going to choose them on the first run because it's almost like duplicating variables. There's a couple of advanced options here. They're very specific for very specific use cases. If they make sense to you, great. If not, you probably don't need them. So now we'll just add a couple of browse tools here and give this a run, and we'll start to look at our first model. All right, so the top output here, this is our model object. So what this is doing is it's using R. This is the script that's run through R that creates the model. Okay, so this can be useful if you want to use it in a later step, which you'll see here shortly, or if you ever wanted to save this model off to use in the future, or for reference that, yes, this was the model I used on January the 19th to do my training class. So that's all that is. It's the name and that model object. The bottom browse is the summary of what the model is actually doing. So what we have here is it starts with the call, and this is the actual call that's made to R in order to build this model. So if you need to ever reference this, or someone in your organization wants to know exactly what was sent into R, this is that call. These residuals here, this is kind of a summary of the error within the model. We're going to ignore this for now because I'm going to show you how to calculate error on a record-by-record basis when we get farther along here. The coefficients, this is the guts of what's going on here. Okay, so the first column has our variables. And you'll see that we have a lot more variables than we actually put into the model. We had income, age, reference, educational, family, size, structure, children, and urban, and now we have all of these here. Okay, and so that's because by default, a linear regression model is going to take a categorical variable, such as educational attainment, and it's going to create a dummy variable for each specific category. So you see we have one for high school grads, one for some college, one for bachelor's degrees. So it breaks it apart and it creates a dummy variable for each one. Okay? Be aware that it will also leave one of them out. So if you notice here, no school, number one, the number one reference, doesn't exist. All right, so it's always going to hold that one out so that you know that if all 5 of these are false, that other one is true, and it serves as the baseline for the model. If you understand that, that's great. If not, that's great too. The next column over here, this is the estimate column. Okay, so the way to interpret this for a numeric variable, such as income, is that for every 1 unit that income goes up, food away from home is going to go up this much. So if we move the decimal over 3 places, we've got 0.009, which is pretty close to 1 cent. So in essence, you could say that for every dollar income increases, that person spends an extra penny on food away from home. For a categorical variable, it's a little bit different. Now we're comparing each one of these 5 buckets to that baseline, which, if you remember, was no school. So what this is telling us is that a high school graduate is expected to spend $500 more on food away from home than someone with no school. Okay? So, and as you know, someone with a bachelor's degree would spend $880 more than a person with no school. So no school is that baseline that all of these are compared against. So that's kind of how you would interpret this estimate column. All right, I'm going to skip over here to the last column, the p-values. All right, so these are tells you how significant each one of these variables is within your model. Okay, so you notice, you're going to notice that the smaller the number, the better, and the more characters on the side here, the better. These characters identify the level of significance. There's the codes that kind of correspond to that down here. So you know that anything with no code has no significance whatsoever, period, star, 2 stars, 3 stars. So the more characters that are on the side, the more important those variables are. Ideally, you would want most, if not all, of your variables in your model to have some statistical significance. In this case, we only have 3. So right there, that tells me that this isn't a good model, and I would move on and try something different. We're going to spend a little bit more time going through this report just so you can understand a couple of other things. Regression is interesting here in that the significance of one variable is almost always dependent upon the other variables in the model. So if I go back in and I remove, say, family size, the significance of these is going to change. It could get better, it could get worse, but the significance of all of the other variables are going to change as a single variable is either added or removed from the model. So all of this other information is valuable. There's some charts over here on the other tab. But the biggest bang for your buck is the adjusted R-squared value. This tells you the true predictive power of your model. Okay, so in this case, or in all cases, it's going to range between 0 and 1, and you want to think of it as a value of 1 would mean that the model describes 100% of the variance. So it's spot on. The closer to 1 you are, the higher percent of variance in the target variable. So the closer to 1, the better our estimate ends up being, the more closer to actual. So as the target variable changes, whether that expenditure variable goes up or down, this number explains how much of that movement is explained by our model. So at 0.26, we're not too bad. What's a good number? 0.26. It's not a bad number, but it really depends. Some people say that 0.2 or higher tells some level of significance. If you take a stats class, that may be something that that you're taught, you want to have at least a 0.2. Others will say 0.3. Some will even say as high as 0.5. It really depends on your business and what you're trying to predict. But know that, this isn't great, but it's definitely, there's some significance in the variables in our model that have some predictive power. Okay, this p-value down here, this is the overall significance of your model kind of as a whole. So the lower this number is, the better. So if we go back here and we're looking, like I mentioned before, we have 3 variables that are significant and a whole lot that are not significant. So let's go back into our model. This would be the next step when I said I wasn't going to go any farther right off the bat. We go back into our model and let's start removing some variables and try to get it a little bit better. So let's go ahead and we're going to remove educational attainment and family structure. And then we're going to add in our 2 variables that we created. Okay, and let's see if that does anything different to our model. We'll give that another run. So last week we had a feeling that some of those, some of that educational data wasn't going to be all of that significant, so that's why we went ahead and created those variables in the first place. So let's take a look and see if they actually help us. So now we see we have 4 variables that are significant and only 1, 2, 3, 4, 5 that are not. So 4 out of 9 is a little bit better. Our adjusted R squared is still at 0.26, but technically speaking, this is a better model because we have more variables that are significant and less variables that are not. Okay. From here, next steps, we could go back in and remove another variable and then run it again and see what happens. Add one in, back and forth. Perfectly reasonable way to kind of go about changing around your model. But in this case, there's an automated way to do this, so we're going to go down that path. And we're going to use the stepwise model. All right, so what the stepwise model is going to do is it needs 2 inputs, where our original here, the linear, only uses 1 input, the data. This one needs 2. All right, so it can't be run by itself. It needs to have a model preceding it. So this is where that object, that model object, comes into play. So if I connect my model object to one of the inputs, it doesn't matter which one you connect this to. Inside each one of these predictive tools, it's a macro. It uses R. R will recognize which one is the model, and it will use it the way it's supposed to. So the model object goes into one, and our data will go into the second one. So what the stepwise is going to do is it's going to use the same data or the same variables that we had chosen in the linear regression model. So now I'm going to give this one a name. We'll call this our step linear model. Okay, and there's a couple of options here. So the search direction. If you were to choose backward only, what this is going to do is it's going to start with a full model with all the variables that we had here in the linear regression, and it's going to go one by one and remove those variables until it can't improve anymore. By choosing both backward and forward, what that will do is it's just like the backward is it's going to remove the variables one by one, but it will also look to add back in variables that were previously removed. So it's kind of related to the idea of multicollinearity, where you have 2 variables that are similar, and it removes one, and then it goes and it removes the other, but the first one may now be significant based on what's going on in the model. So it goes back and forth, picking and choosing variables, adding and removing variables to determine the best fit. Speaking of fit, the last other option here is the fit measure. You have this is the Akaki method and the Bayesian method. Typically, the Bayesian method offers a model with fewer variables, and it's a much more stricter model. But feel free to try both, see what you get, and go from there. We're going to keep it as the Bayesian, or as the Akaki for now, and we're going to give this a run, and we're going to take a look at what our new model looks like. All right, so very similar looking report to the one we just looked at with the linear regression. It's just the model is a little bit different. You'll notice that all the variables are significant this time. So what the stepwise is doing, like we said, is it's going in and it's picking and choosing which combination of variables is a best fit for the model. You want to just check and make sure that they all make sense, and that they're all positive. These are the only ones that matter. These 4 variables are the only ones that matter in this model, and the only ones that are going to have any effect on that target variable. You'll see our R-squared is still in that 0.26 range, and that p-value is still about the same, nice and small. Okay, so that's what this report looks like. So let's say I'm happy with this, okay? I'm not thrilled with 0.26, but just for the sake of it, let's say I'm happy with this model. Now I want to score this model to see what it looks or what it does to my data, and then I'm going to calculate the error to see just how good or bad it is. So I'm going to pull the score tool down, and I'm going to connect that, again, 2 inputs. We're going to need a report or a model object, and we're going to need data. Again, it doesn't matter which one goes where, but we want our model that we like best, which in this case was the stepwise. We want our data. So I'll connect my data in there like so. Your data must have the variables that the model uses in order for the score tool to work properly. So in this case, we didn't do any modifications. It's the same data stream going into the stepwise that's going into the score tool, so we have no problem there. Put a browse here. Some of the options, we'll talk about these more in the next example, but if you oversampled your target field, you would check that box. If you want to see confidence intervals, you could go into these boxes here. But for this, we don't need to do any of that. We're just going to give this a run. So just a note here, the stepwise model, it only thinks about the statistics when it's determining the model. It doesn't really put any theory behind it. So while it may produce a model that is statistically the best, it may or may not seem right for your business sense. For example, if this was to tell us, just to go back here, if this was to tell us that as income went up, the estimate on food away from home spend went down, that doesn't really make a whole lot of sense, right? I mean, typically speaking, the more money you make, the more money you're going to spend. It's just kind of nature. So if that's what this was telling you, you would want to remove that variable from your model. Okay, so here we're done running here. We'll take a look at our output from our score tool. All right, and you see, so here's my score. And what this is really giving me is the actual predictive value of food away from home. So this number, $1,900, compared to the actual value of $700. So we're a bit off, not even close, really. But there's an easy way to compute just how wrong we appear to be, kind of on a record-by-record basis. We can do that with a formula, with a simple formula tool. So I'm going to drop that in line here. We're going to create a field called error. And simply, it's going to be that predicted value minus the actual food away from home value. And that's going to give us basically the difference. So how far off we are. A positive number is going to mean we're high. A negative number would mean we're low. But those are really still whole numbers. They can be a little bit deceiving. So I like to also calculate my percent error. And for that, I'm going to take that new variable that I just created, error, and I'm going to divide it by my actual. And then we'll give this a run. Take a look at our output. All right, so you see here, our error numbers are off by quite a bit still. What this percent error is telling me, that this one here is 173% wrong. This one is 271% wrong. So this model is really wrong. Even though, going back to here, our R squared was pretty good. It was in the realm of significance. The model definitely still needs some work. Other steps you could try adding some more models to it to see if you get one that looks better. You could try the decision tree or a forest model. You could try altering the variables, adding and removing some to see if you can get a better fit. But that's basically kind of where we're at with this one. I want to go ahead and I'm going to save this. Save this out here. This is my RE model build. All right, that's helpful. Okay, sorry about that. Okay, so on to the next data set here. We're going to start a brand new model, and we'll need a brand new input tool to pull that second data set out. If you remember from last week, that's our TM model input for target marketing. In this case, we had our status field, which is a 1 or 0 based on whether or not this person is or is not a customer. And we have a segment score, which is some transformation of the experience variables. And then we have a number of kind of yes/no variables, and then a couple of transformations of that segment score that we did last week. So we took the log of it, we took the square of it, and we took the square of the log, just to look at it a few different ways. We're going to look at a few different modeling techniques here that are used to predict yes or no. But first, in this example, we're going to create samples. All right, so in the data investigation tools, there is a create sample tool. So we're going to pull that out first. And what that's going to give you is 3 outputs: an estimation, a validation, and a holdout set. It's always a good idea you don't want to build your model with the same data that you validate your model, because there's always that that chance that your model is really good at predicting itself. But when you take it outside and you try to apply it to a different data set, it could completely bomb or something like that. So in this case, we're just going to make this 50-50 so that we get half in our estimation and half in our sample. This random seed makes sure that every time we run the workflow, we always start at the same point, so our 2 sets of data are always the same. So we're not getting a different 50% each time. Okay, so now our first model that we want to use here is going to be the decision tree. I'll pull that one out, and we want to connect it to the E. All right, so that's our estimation data set. You want to make sure that that is the one we use to do all of our model building. Excuse me. All right, so just like the other ones, we want to give this a name. Just call this decision tree. I don't know if I mentioned it earlier, but you want to make sure, since all of these use R, you want to make sure that you follow the same rules within our language, where you don't want any spaces in your names. Okay, so make sure that you can stick an underscore in there, but don't have any spaces in your name. All right, our target variable here, okay? In this one, we're predicting the target variable is their status field. That's yes or no. Is it going to be a customer or not? But notice that all the fields are available to me here. That's because the decision tree doesn't really care if it's a numeric value or not. You can use it for either type. So that's why all of our variables are present. A cool thing about the decision tree is you can give it whatever variables you want, and then it's going to kind of decide which one makes the most sense for your model. So even if I go ahead and I give this all of my variables, it will go ahead and take them and determine which ones are not important, and it will just not use those inside. You notice I'm leaving off the segment transformations. There's no need to include custom variables in a decision tree because it can use these variables as many times as it needs to as it goes through the tree process. So by having that same one in there more than once, it's essentially the same variable, just a different, just being transformed. So you don't need to use those in this case. Down here, we have the complexity parameter set to auto. That's fine. We'll talk about that again in a little bit. There's a lot of customization here. They're all a little bit more advanced. Again, if you understand this stuff or you're interested, feel free to go ahead and play around with these. The graphing options, one thing we'll look at in the next phase is this uniform branch distance. For now, we're going to keep them uniform, and then I'll show you what those look like after when we change it. So I'll give my outputs, and we'll give this a run. We had time, we're doing good. Okay, so you notice here we have 3 outputs. That's because the decision tree has this new interactive feature associated with it. So what we end up with here is this cool looking interactive tree where we can kind of click through. You can't really click through, but you could hover over the different points and see what's going on. You have this variable importance plot where you can see which variables are important in general, and then how much more or less important they are than others. And then we have the confusion matrix here, which looks at the actual and the predicted and how many of them kind of line up. So the actual ones that we predicted as ones at 1,600 of them. The actual zeros that we predicted to be zeros was at 1,000. We've got a little bit of variance here. The middle one is our report. Much like the other reports we've looked at, it starts with the call, which is the R script. Here we have our root node error right here. That basically is if I was to pull a record out of a hat, what are the chances that it would be a customer versus a non-customer? So we're pretty much 50-50 one way or another. If I wanted to calculate the error of this model, for instance, there's no R squared here like there was in the other models, but what I would basically do is take my root error and multiply it by the lowest relative error or X error, either one, but the lowest one. So if I was to take my 0.5 times my 0.75, I'm looking at roughly 38% error. It's kind of how you'd compare it to an R squared, but it's not perfect. This leaf summary is kind of the longhand version to explain what's going on in the tree plot down here. Because as you see, the tree plot's going to cut things off, so we just get segment underscore. If you had multiple variables called segment something, then you could get confused, and then you can go up here to the summary and see what's going on. If we look at this tree plot, it starts off, everything that goes to the left is a true response. Everything that goes to the right is a false response. So the question here, so this is these if-thens. So segment score is less than 50. So you see that 78% of my records are non-customers. So when segment score is less than 50, there's a 78% of those people are not customers. So that's kind of that's a pretty obvious reason to not go, or explanation for these people. They're not really going to be good targets if 78% of them are not customers. But the ones that are, the 22% that are, come this way. And then we look at where segment score is greater than 149, okay, or less than 149. So we're looking at segment score of greater than 150. At 62% of those people are customers, right? So that's a good variable for me. So when segment score is greater than 150, 62% of the time, those are going to be customers. So it's an endpoint of the tree, but it's also a good predictor for us. Everything that's in between 50 and 150 is going to come down this middle section here and run through the rest of these branches. We need to know a little bit more about those people, okay? Computer peripherals equal 1 or 0, right? And then down and so forth. You can't change this tree at all, right? This is the model. This is what the model produced, but you can trim it. Okay, you can remove some of these lower levels as you get to be into the weeds of things. It may not be as important. So you can look at the pruning plot here. Generally, when you see this start to level off, you can trim it at that point. And what it'll do is it'll just trim some of these lower branches. You could argue that, here-ish, it's on a decline. Somewhere in the middle here, we'll pick, just because it's nice and easy, it's 0.0076. So what we do to trim this is we insert this number as our complexity parameter back inside the model. All right, so if I go back into my model and I put 0.0076 in as my complexity parameter, it's going to now prune my tree to that step. And while I'm here, I'm also going to go into my options and I'm going to uncheck my uniform branches. So now what you'll see is the longer branches in my tree have more predictive power. You don't really see it so much in the interactive, but inside the report, you can see these nice long ones. So this is a nice long, strong branch where it's saying, 78% of these people are not customers. 62% of these people are customers. That the error didn't really change all that much. In fact, it may have gone up a little bit because we have less branches, so there's a higher error here. But that's kind of how that one works. So that's the end of a decision tree. We kind of get to that point. Now we're gonna build another model with this data set. Right? We're going to build a logistic regression. I'm going to connect this to my same estimation set. The logistic regression needs a name, just like all the other ones. We'll go log mod. Our variable here is our status. You'll notice that this is only accepting string variables. So this is the opposite of the linear. So between the two, depending on what your data type is that you're trying to predict for your target, will determine which one of these makes the most sense. Here, we're going to go ahead and we're just going to select all of these records, except our record ID and our status field, obviously. We're going to have all of our segment scores here, but it's going to sort itself out because when we finish this, we're going to use the stepwise model again. Okay, so let's just go ahead and run this quickly here. Doing okay on time, but I want to make sure I get through the rest of this. Works very much the same as the linear regression model. The report looks the same. Again, your call, your error, notice that all four of those segment scores are here, and none of them have any significance whatsoever. They're basically getting in each other's way. That's why you don't include the same variable several times, even if it's been transformed, because they really just rule each other out and become unvaluable. The coefficients here are very different as far as the interpretation of these estimates. It's really hard to put into words. But basically, if there's a negative coefficient, then as the variable gets bigger, the likelihood of your target characteristic goes down. Okay, so basically just remember that if the number is negative, it's less likely to be for your target to be predicted, and if it's a positive number, then it's more likely. Okay, but to really understand these numbers, the way we did in the previous example, I would go ahead and go searching online for some help as far as understanding that. There is no R squared here. That adjusted R squared value doesn't really exist in this model, but we do have an equivalent, which is this McFadden R squared. You notice it kind of works the same way. It's a little bit more lenient, but we're at a 0.07. Typically, you'd want at least a 0.1. 0.2, it would be even better, but expect this to be lower than your linear regression model would be. Notice that we've got 4 variables with some significance on it here. That's good as well. That'll get ironed out when we put it in our stepwise model, and we'll get even better. We're not going to go ahead and really assess this model, I'm going to show you a better way to assess all these models together once we get this third model built. So the stepwise model, like before, it's going to take the output from that model object and that same estimation set. To give it a name, step log mod. We'll keep this set to backwards and forwards. This time we'll change this and we'll use the Bayesian method just to change it up a little bit. We'll add our browse tools here. And we'll give that a run. All right. So you'll notice that now all of our variables are very significant, but there's only 3 of them. So it ruled out all those segment scores got eliminated, and we're basically here to sit looking at computer peripherals, which is negative. So it's less likely that a person would be a customer if they bought computer peripherals. This G131, this was our variable, our Hispanic variable that we used, or that we created or added last week. Basically what that's saying is that a Hispanic person is more likely to be a customer, and the log segment was the only one that remained. So as that goes up, the likelihood of him being a customer will also go up. The McFadden R-squared is still in that 0.07 range, which is kind of low. I can't really compare my R-squareds across all of my models because, because only the stepwise and the logistic regression have an R-squared, the decision tree does not. So a way to compare models is to use a lift chart. So here in our predictive tools, we have a lift chart. You notice the lift chart also has 2 inputs, so it's going to need a model object and it's going to need data, except we've got 3 models that we want to compare. So what we want to do is we want to stack those models on top of each other using a union tool. So I'll pull that out, and I'm going to connect the O object from all 3, and then run that into my lift tool, or lift chart. Because all of those models have the same file structure, name, object, they just work perfectly into the union. And then I need data. Now this is where I'm going to use my validation set, right? So I don't want to estimate my data. I use my estimation set to estimate, to build my models. Now I'm going to use my validation set to test those models. In this case, now inside the lift chart tool, I'm going to stay with my total cumulative response. True response rate, this is in this target marketing example, you typically end up oversampling one way or another, which we did last week, so we need to adjust for that. So my total true response rate is 2%, and my target level is 1, so now I know what the desired response is. I don't really need to do a sample name or anything like that. So we will add a browse here and run this again. You're going to see a graph here any minute now. Okay, so here's a graph that compares all of our models. You can see they're all very similar. Usually you'd look for the one line that stands out, and that would be your best model. But basically you're looking for the model or the line that has the biggest area underneath it as a whole is the best overall model. But if you wanted to say, if I mailed to the top 20%, I would capture, about 36-ish% of my original customers. So that'd be your lift. Okay, so looks like the step-wise model is the best of the three. Here's your gains table. It'll give you all of your intercepts. And then the area under the chart at the bottom, so you can see that area here. Our stepwise model has the largest area by just a hair over the logistic regression. So our stepwise model is the winner in this case, so that's the one we're going to use to score our data. All right, so now I can bring my score tool out. I'm going to use that stepwise model, and now I need my data again. I use my estimation set to build my models. I use my validation set to validate my models. I'm going to score my entire data set. So I'm going to go way back to the beginning, and I'm going to score that entire data set. All right. Now we're going to have to use these options here. Our target field was oversampled, so we want to make sure that we account for that. Value that was oversampled was the responders that were 1. The 2% was the oversampling was 2%. So we adjust that there, and now we can go ahead and run this score. Okay, now we see here our scored data. We have a score for our zeros and a score for our ones. So what that basically is telling us is this is the predictive value that this person will not be a customer, and this is the predictive value that that person will be a customer. Okay, so they're kind of all over the place here. So typically it makes it a little bit easier to sort it. So we can go ahead and use a sort tool. We're going to sort on our yes, they will be a customer, and we'll have that descending. And then, we're looking at, it's target marketing, we're looking at mailing. So say maybe we saw something in the data here that said that, the top 25% of our people made the most sense to mail to. So we can grab a sample tool and we can filter this off to take the first 25% of our data set, and then we can give that a run. And then you'd essentially have your list of customers to go ahead and mail to. So that kind of sums this one up. A couple other things I want to quickly touch on as we are out of time. All of these predictive tools are macros that use R. If you are good at R, if you know R, if you can write R code, to get to those, what you can do is right-click on any one of them because they're a macro, and you can open that macro up. And then inside, you will see all the guts of what goes on in the logistic regression tool, for example, and you'll find the R tool. And inside the R tool is all of that code that's in R. Okay, so if you know and understand R code, you can actually modify this to your liking or build a tool from scratch and then just save it off as your own version so that you can use it for whatever. Okay, so that's the end of the model building exercises here. Just to quickly summarize, we talked about linear and logistic regression. Your linear regression is going to be when you have that numeric value that you're trying to predict, sales, food away from home, etc. Logistic regression is going to be the best for a binary target, yes, no, some kind of a predictor or something like that. Some resources. If you need further help, the Alteryx community is always a great place to go. There's lots of very, very bright people on there, Alteryx employees as well as customers and partners. Lots of activity. There's posts, blogs, great way to find answers to your questions. Training resources are always available. That's where you went to go to sign up for this class. Go back and visit that page again and sign up for some additional classes. And then there's always technical support. You can email clientservices@alteryx.com and someone will get back to you and help you with whatever problem you have. There's the live chat option. If you have a simpler type question, you just can't get your formula tool to work right or something, that's a great avenue to go down. And then there's always the phone. You can call client services and speak to someone directly. That's all I have at this point. I just want to let you know that upon the end of this session here, you'll be directed to a survey. Please take a moment to fill that out. Let us know how we did. Again, I apologize for technical difficulties at the beginning and running a little bit late, but I hope you got everything that you needed out of this session. Thank you again, and enjoy the rest of your day.